What's up, you guys? It's Coney1553 here. So last episode I was talking about this giant thing right here. As you know, oh great, the weather just changed. Give me a sec, let's put the time. Alright, so anyways, as I was saying, this gigantic wall full of just a bunch of AND gates made diagonally so that each column represents the same value in binary, and I would need to add all these up, and this can do multiplication, but you gotta add up all the partial sums, and that's what takes the most time, adding up the partial sums, right? So I've made another circuit, kinda. Let me try and explain this circuit. I'll try and explain it a lot better than most of my other circuits. Let's do another wall here. Let's make it nice and obvious. Let's do it like this, I guess. Alright, so let's say I want to do 5 times 5. What would happen? So here, let's say I have, okay, 5 times 5. You do 5, then you multiply it by 5. Now what would you do? You would do, first thing you would do is 1 times the whole number here. So your answer is going to be, if you write it down, we're going to write it down actually. We're going to do 101. That's the answer. Then the next part, yeah, let's just put it here. So then we're going to do, actually, let's put it right here. Let's try and see. Okay. So we're doing 1 times this whole number. Then we shift a digit, so we're going to add a 0, right? Because you got to shift a digit. So then we're going to do 0 times everything, so we're just going to get 1, 2, 3, bunch of zeros. Then we're going to shift 2 digits, because we're at the third one. And we're going to do 1 times the same number, so we're going to do, actually it's going to be 101, and then we shifted 2, right? Now, from here to there, this is our partial sums. Let me actually write that correctly. Let's do 101, 1, 2, 3, 4, 101, 1, 2, and then add a 0 here. And we need to add this together. So this we're multiplying here, 101, and we're multiplying 101s, and we're doing multiplication. Let's do it like this. And over here, this is partial. Let's put an R there. There we go. Partial sums. Let's put a capital S like that. I think that's good. Let's do that. So this is our partial sums. Now, if we add them up correctly, here's what we will get. We're going to do 1 plus all of these zeros. So we're going to get a 1 at the end. So we're going to get a 1. Then we're going to do all of these zeros together. Then we're going to do this guy with this guy. It's going to do a 0 because 1 plus 1 in binary is 0. Then we shift it over, so we're going to get a 1 here. And then we're going to do 1 plus nothing. So we're going to get 1 because the 1 plus nothing. Then this here, we got a 1 from these two right here. Over here, we have nothing. Well, over here, we have nothing because we carried over our 1. Over here, we still have nothing because we added 0 with 0 with 0. Over here, we just added 1 plus 0 plus 0. So this is the answer. And this is a 1, 2, 4, 8. So 1 plus 8 is 9, and 16. And 16 plus 9 is 25. So this is 5 times 5, and we do, in fact, get 25. And this is the part that takes the longest time. It's not generating the partial sums, because that's easy. We can do that all in 2 ticks or 3 ticks. Yeah. So 0.3 seconds to do all the partial sums instantly. Almost. Kinda. Because I have like a torch tower going on here. So kinda. Anyways, what takes a long time is adding all of these up. So here's another way to do it. When you think about it, the number on top or on the bottom depends how you want. Like I'm always using the one on top, and I'm shifting the one at the bottom. And what we're doing is that if we're doing 1, 1 times this, well, we're just going to copy paste this number here. Now if we're at the second digit, well, we're going to copy paste this number if it's a 1, but we're going to shift it by 1. If it's a 0, we're just going to add nothing. And if it's again a 1, like at this place, then we're going to copy this, but it's going to be shifted by 2 because it's like the third number here. And if it's a 0, then we're just going to add 0. So if you think about it, we could have, let's say, a beautiful register, a shift register. Let's say 4 bits. Actually, how many bits of a number? This is a 1, 2, 3, 4. This is a 5-bit. Let's do a 5-bit register. 1, 2, 3, 4. Let's do a 5-bit, but let's do 1, 2. So we're gonna have our first register have a 5. Second register is also gonna have a 5. We're gonna put it at the same height. Alright. Now this is step 1. You put in the 2 numbers you want to multiply in the register. Now step 1 is that we're going to have an adder here, let's say, and the number is going to go through the adder if and only if the first bit here is a 1. If it's a 0, it's going to do nothing. If it's a 1, we're going to add it to the adder, okay? So we're going to send this to the adder since it's a 1. So let's actually get rid of this. Let's move that all the way up here. So we're going to do 0, 0, 1, 0, 1 like this. And then we're going to do 0, 0, 1, 0, 1. And since last bit is 1, so add to adder. Let's do that. So now we're gonna have this right here is our memory. Let's do that. Let's do the memory of the adder. Memory of the adder. Okay, like this is our result, kind of. So far our result, since we added to the adder, we have 101. Pretty neat. Now what's the next step? Next step is we have to shift. So this number, we shift it no matter what. So we're going to shift it by 1. So we're going to have this. This is what's going to happen. So shift number. And we're going to do one like this. Pretty sweet, because we just shifted everything to the left. So it's a left shift. This guy, we already used the last bit. So we're going to do a shift number again. But we're going to do it to the right. And this guy, I'm going to rewrite it. We're going to shift number to the left. And we're going to do 0101 just to show it. This is shift number to the right. And what's going to happen is we're going to have 1, 2, 3, 1, 0, like that. There we go. And because of that, since it's a 0, we add nothing to the adder. So we're gonna do I'm gonna write it down again. So shift number to the right, so it becomes 00010. Last bit 0. I should actually write the whole thing up here. So shift, because I'm gonna run out of space. Shift number to the right, 0. So last bit 0, add nothing. So our memory is still gonna have 101 because we added nothing to it. Now the next one we're gonna do again, shift number to the left. So we're gonna have 10100. Because we shifted again to the left. Now this number, we're going to do it again. Shift number right. Again. It's going to be 1, 2, 3, 4, 1. And then we're going to do last bit. If I could put an A, last bit 1. So add to adder. That's what I wrote last time. So then we're going to do this plus this. So what is that? So we're still gonna have our 1 here. When this 1 right there is going to match with this guy, so we're going to carry over. So we're going to have 1 1, and we're going to have 2 zeros, I think. Yep, and a 1. Just like that. And then we could shift again. So we're going to, again, do it. It's going to do that step again. So shift number to the left. So it's going to become, if let's say I do have a 6-bit register, it would be 101 and then 3 zeros, right? If I had a 6-bit register, let's imagine I do. And let's imagine we do shift it again to the right. So shift number to the right. What's going to happen is we're going to have 1, 2, 3, 4, 5. Basically our register, okay? It's going to be empty. Since it's going to be empty, register empty, stop adding. We're going to stop adding, and the answer, this is answer 11001. Pretty neat. So this took a few steps. This is another way of multiplication. What we're doing is that every time we calculate a new partial sum to add to the adder, we add it all like right away to the adder. So we're doing it one at a time. Instead of having all of our partial sums calculated at the same time, and then we add them all together in parallel, what we're doing is we're doing this kind of in series-ish, or we're doing this by depending on a clock. What I mean is we're going to have a clock that's going to be pulsing the shift registers to shift their numbers left and right, and we're going to have some memory being clocked to refresh and remember the new partial sum calculated, and we're going to keep adding our new number to this partial sum until we have nothing into the register that we're always shifting right. And when that happens, we're going to do a stop. We're going to clear this register, because this register could go on forever, technically. Let's say if it was 32 bits long, and this guy's already over, but this guy, he's going to keep going for the next, this is 1, 2, 3, it's going to go again for the next 29 bits before it's empty. So we're going to have a way of detecting that it's going to be empty. So we're going to let this guy shift completely everything out, or we're just going to override this to clear itself. And we're just going to send our answer to the screen, and voila. Now, it's a good thing that I took a lot of time to explain how this can work, because I already have a prototype, even though it's not perfect at all. So let me just try to explain what's going on here, because you guys are probably looking at this and like, okay, why does it look like a giant hammer or a T or a croquet thing? Mallet, that's the name to play croquet with. Anyway, this is one of my registers right here. This is the register that would shift my number to the right, making it smaller. And this is the other register, this whole thing right here, that would shift my number to the left, making it bigger. Now over here I have some comparator logic. This is just to clear the display. Well, actually this is telling my adder, hey, the last bit is a 1, so add the number from this register to your partial sum. Sorry. If it's a 0, the comparators don't let the signal go through, because this whole wire turns off, and all the comparators receive a signal strength of 15. So since they're in subtract mode, they are going to add nothing. So basically, we're just not reading from the register. This is a way of doing that with the comparators. It's actually quite small, and I'm happy about it. Now, the way you input your numbers, that's a bit tricky, but it's not too tricky. I can show you that in a second. This is the normal adder. The issue with this is that the adder is pretty slow, which is why this whole thing needs, like, it works, but you gotta do it manually. You can't put it on a clock yet. I need a better adder for it, and I'll explain it to you guys in a bit. So first off, let's clear the memory. Same comparator logic if all the comparators are in subtract mode, and I would like to save a new number, but actually let's just clear this register first. Let's run the clock, because right now I have a number that is right here, and it's slowly shifting along. As you can see, all those little redstone being lit up. This is my number. So I believe the memory is empty. Yeah, this is just a regular memory that I use in all my other builds. So first off, you put the memory so that you can actually write to it. Let's say I want to do 5 times 5, right? So we're going to do 5. This is 5. Now we need to add it in, but we're going to add in the second number 2. Let me just set the time to day so you guys can see better. Set 500, or let's do 400. Let's put it earlier, 400, why not? Sorry, oops. Let's do a 5 here too, so this would be 5. Now, we just need to clock our register one time, so this button does that. It clocks both registers, and it's fully in sync. Now, you turn off these, because we're going to keep clocking the register, and we don't want to keep adding data to it. So now this is 5. As you can see, this is 1 and 4 right here. So is it here. This is 1 and 4. Now since this is 1 and right now we have 5, we're going to add 5 to one of the partial sums of the adder, which is already ready. So we can right away, right off the bat, already save it to the memory. So now once we saved it, we need to shift both registers one time. Let's do that. Sweet. Now, the next one is a 0 since the 1 is gone. Now it's a 0. So since it's a 0, even though we shifted this 5 here, all of the comparators are not reading this because we're doing this times 0. So we're adding 0 to the adder. So once again, we can clock the adder's memory if we want, because right now we're doing 5 as one of the inputs and we're just adding 0. So 5 plus 0 is still going to be a 5. Then clock this one more time. Pretty good. Now we're having the 1 again, 101, that last one. And we shifted this a bit one time, and then we have our number coming through, as you guys can see. And we're already adding with the previous 5 that was saved. Now we just need to clock our memory one time to save our new partial sum with the previous partial sum. And as you can see, this is 1 plus 8 and 16, which is 25. So the multiplication is done. Donezo. The problem is, let me show you what the problem is. Now let me just clear this first thing, and let me also just clear off the whole register. I think I was trying to do 15 times 15. Now 15 has 4 partial products, whereas 5 times 5 has 2. And 15, since it has 4 partial products, basically every time it shifts until the register that shifts to the to the right, sorry, until this one that shifts to the right, if you're reading your number like this, until it's empty, it's adding a partial sum each time. And each time there's very often a carry out that needs to be calculated. And calculating that carry out takes time, and sometimes it's not done calculating the carries and there's already another number coming through. it's not done calculating the carries or the final partial sum before adding the next one, and we're clocking the memory before it's done. And since we're doing that, our answer that is saved in the memory is not correct. My clock would need to be really slow. The slower, the better. Let's put it really slow. That's the solution. The solution would be to add a slow clock so that it can give enough time to the adder to refresh itself. I hope that's enough. I hope it's slow enough. If it's not slow enough, I'll have to make it slower. But this would be the main solution, making it slower so that the adder can have enough time to calculate all the carries. But that's not what I want. I want the fastest clock possible so that we can multiply it like super fast. I haven't calculated this. I am not kidding. Let's say I do calculate this. I'll do that right now off paper. So give me a sec. Yeah, so after like probably a good 20-15 minutes of trying to think and calculate, there's gonna be 1,858 additions being done in total before you sum up all of the partial sums. You would need to do it, I think it's more than that, but you would need 1,858 additions. That means adding up all the partial sums and also all the carries, adding them all up to that partial sum. And like I said, this guy, he does that, and no matter what, it's always 32 partial sums. Of course you get some carries, but the carries get calculated before you add the next partial sum. So I would like to thank you guys for watching. Hope you guys enjoyed. Hope you learned. I'll see you guys in the next one. Take care. Bye bye.